Hello and welcome back to Calculus 1, section 5.3 on fundamental theorem of calculus. What's going on? Well, fundamental theorem of calculus consists of two parts. And part one, you already know. So this is known as FTC. And part one is that the definite integral a to b of f of x dx is the antiderivative capital F of x computed from a to b, which is equal to f of b minus f of a. So you already know the first part of fundamental theorem of calculus. It's a definite integral, a way to compute definite integral. We already said that it can compute area under the curve. It calculates accumulation. And I'll give a word problem eventually so you can understand that. And it's just, the stuff that we did in a 5.2. It's the part two that we need to focus a little bit on. And this one says, lock the doors, the derivative of the integral of a to x of f of t dt is equal to f of x. Note that it's a lowercase f everywhere. So some might say, what's the point? I just changed the variable from t to x. Yeah, that's exactly the only thing that happened. We literally changed the variable from t to x. Because if I get to use the same lowercase letter, that's the same function. That's the same function. I'm going to erase this. I'm going to write it and then erase it. So if I have that my f of x is, let's say, x squared plus 3, then my f of t is t squared plus 3. The f of a flower is a flower squared plus 3. It doesn't matter which variable you have, right? So what's the point of part two? Well, let's first verify that part two works. So, derivative of integral a to x of f of t dt, copy the derivative, and now, when you integrate, you get your f of t computed from a to x. And now, you have your f of x minus f of a. And then, when you take the derivative of this one will go to lower f of x minus, when you take a number a, whether that number is 0 or 1 or 7 or whatever, and plug it into f, you're going to get a number there, right? So that's constant. So it's going to be 0 over here, and you just get f of x. So we did this calculation, and we did get f of x, which is what the formula promises up there. So can anyone tell me, why are we writing this? Why do we care? Why is this fundamental theorem of calculus? What is so fundamental about it? What is this trying to tell us? If we know that this and this is the same thing, just with a different variable. Why do any of this? Go. Do what?
Is it taking the derivative? Is just canceling out everything else?
Canceling out? What do you mean everything else?
Say the question again, please.
Why do we care about this? Why? What's all of this about? Why is this so fundamental? Why would it be fundamental? Why is it not a theorem? Yes.
Why do you not get the same results when you have A and B? Because I feel like
when you have numbers, well, look, we had a variable in the limit. See, there is a variable x in the limit, so it's not a and b, it's a and x.
So if you're given only one of the variables, then you use the second one. But if you're given both of the numbers, you have to use the first one.
No, the definite integral computation, you use two numbers, right? They're all in limits.
Right.
But now this one has a variable and a number. So, and I use the variable and a number. You see over here I plugged in a variable, over there I plugged in a number. And then I got still a function, and this one goes to 0. Yes?
Is it taking a derivative of the antiderivative?
What do you have? Yes.
Oh, I was going to ask, so it's as x approaches a, or as a approaches x, right? So
It's from a to x. That's that's the interval.
So, I mean, isn't it doing essentially what we do without?
Nope. Max, what do you have?
So is it taking a derivative of an antiderivative?
Yes. It's that simple. You are taking the derivative of antiderivative, they just cancel out. And you are left with the function.
By canceling everything.
Yeah. That's all it is. You are taking a derivative of antiderivative. This particular formula tells you that derivatives and integrals are opposites of each other. They undo each other. They're opposites. That's all it says. And that is the most important thing, right? With functions, you have inverse functions, right? The function that will undo another function. With numbers, you have opposites. For addition, 3 and negative 3 are opposites, because when you add them, you get 0. For multiplication, you have 2 and 1/2 as opposites. When you multiply them, you get the identity, 1. So, if you bring that now to the level of functions, what operators are opposites of each other? Well, derivative and integral are opposites of each other, because when you differentiate and then integrate, you go back to the, right? So think of it as inverting the sweater and then inverting it again, and you are back where you started. You what?
It's funny, invert the sweater.
Yes, right?
It works.
If you take the sweater up over your head, right, it's going to be inverted, and then you go in, pull the sleeves out, and right side up. You are all familiar with that, I hope, right? So this particular statement here says that these two are opposites of each other, and that is a huge deal. Now, we did define integrals as antiderivatives, we learned them as antiderivatives, and now we write that in a formula, mathematical formula, which says that these are opposites, which means that when you integrate, you can use derivative to check. You can go back to the original problem. If you differentiate something, well, the integral will bring back the function that you started from. So this formula tells us that derivatives and integrals are opposite. And now, I would like to write the two formulas and ask you why. Or actually, why? Right? Giving that kid from the previous section. So, f prime of x is defined as the limit h goes to 0 of f of knockoff in x plus h minus f of x divided by h. And your integral from a to b of f of x dx is given as the limit n goes to infinity summation 1 to n of f of xi delta x. These are the two formulas that you learned. So one is for the derivatives and the other one is the Riemann sums for integration. How are these opposite? Why do they undo each other?
It's rate of change times the
Well, one is rate of change, the other one is accumulation. So we don't pull anything from there. Just look at the formulas. So why do they undo each other? They're both really, really small because h goes to 0, it's really small. Delta x is going to 0 as well, as n goes to infinity, because delta x was defined as b minus a over n. So as n goes to infinity over here, delta x is going to go to 0, and h goes to 0 as well. So both of these driving factors, h and delta x, are very, very small. And so that's actually the feature where they get to be the same. What is the stuff that makes them completely opposite of each other? Now, it's way too simple, which is why you're... Thank you! That's it. One is division, and the other one is multiplication. F times delta x. Over there you have f divided by delta x, form of delta x, right? Great. What else?
sum and minus.
Exactly. Yeah, it's a subtraction, right? And the other one is sums. Perfect. And then some of the really obvious stuff. Oh, the limit goes to 0 and the limit goes to infinity. Okay, fine, I'll take that one too. But, but yes, they're opposite operations of each other. The one is division and subtraction on the derivative, and the other one is addition and multiplication on the, right? So there is a multiplication. Let me write it in blood right here. F times delta x, right there. X times delta x. So do not, comma, under any circumstances, comma, forget your dx's and dt's ever, because you trigger my allergies and then I'm just become allergic to you, which is a problem. So integral f of x dx, because it's times dx. There's your height, there's your width. And if you write it this way, well, this has no meaning in mathematics or anywhere else. And that's obviously a problem. So, yeah. Now, the last thing that I need to ask is area under the curve, the same concept of as definite integral, and the answer to that is no. If the function dips below x-axis, then you have the definite integral value and area value to be two different numbers. You have to, from the concept of your problem, you have to figure out whether you are looking for definite integral or area. They are the same when the function is above x-axis. They are different if any part of the function dips below x-axis for any amount of time. So that's something that you have to be very careful with as you move on. in terms of concepts, the derivative formula on top is calculating rate of change, and the integral on the bottom is calculating accumulation. And they work differently. Now, you will have a lecture on this in Calc 2, but just for the sake of those not going to Calc 2, if you talk about population, you can have your model start with, I don't know, 500 rabbits and then e to the 0.03 t. So here's your population for, let's say, multiplication of 500 rabbits. Right? You put 500 rabbits somewhere, give them all the food, make sure there are no predators, they will multiply exponentially. So now, what can you calculate? If you do calculus, you can do the limit as time goes to infinity of the p of t, and that will tell you how many rabbits you're going to have after infinite time, and that's a lot of rabbits, because you will have infinite amount of rabbits. So this is not a good population model, but, right? So, will tell us number of rabbits. So let's say this is a rabbit population, after infinite time, which in this case is infinite rabbits. The the p prime of t will tell us how many new rabbits we add in a particular year. So it's the rate of change. If your t is, let's say, 2019, then if your t is 2019, that means, oh, this is going to work perfectly now. Oh, no, actually, no, it won't. Yeah. I mixed up the Christmas and Easter and rabbits. Yeah, because they're 30 plus years apart. Anyway, go on. Never mind. So, what you have is population of rabbits. And if I have t to be 2019, then that means that 500 was when the year 0 was. So we had 500 year 0. You can plug in the original equation 2019 to see how many rabbits, if those were left to their own devices, how many we would have today. And then you can go and you can plug in, you find the derivative of the population. It's just a simple exponential function. You find the derivative and you plug in a year, any year you want. It will tell you how many more rabbits were added in that particular year. But then you can find the integral of p of t dt from a to b, which is time 1 and time 2. Time 1 and time 2. Will tell you the total number of rabbits, of all rabbits, from time 1 to time 2. So you want to know what is the total amount of rabbits that we have from year 1950 to 1963, whatever, right? Those 13 years. and you can calculate that with the integral. Now, there will be a lecture about this stuff in Calc 2, so you will have more exposure. So now we see what the calculus is. You saw limits, you saw derivatives, you saw integration, and each one of those calculates specific things. Now, if I want to apply this to a medical field, I can have an exponential model with a negative sign metabolizing a drug in a body. If I want to go in the business field, economics field, I'm just going to call these dollars, not a population. Take a look at accumulation of money. How much money am I making per year? How much total money do I have from year 3 to year 5? So all of these concepts are very useful, right? And this is why calculus rules technically everything. So you can't do any of the science, you can't do any of the serious economics and business and any of that stuff if you don't know basics of calculus, because calculus is the study of change, right? Study of change and accumulation and predictions, right, of what future brings. So we use calculus all the time. So now we're going to restart the stream for the 5.4. I think it has a funny title, Working with Integrals. So we're going to take a look at a few formulas, some of which you absolutely must know, and some of which you, like a quality of life, formulas. So if you know them, your calculations in the future will be faster. If you don't know them, well, you just brute force calculate without those formulas. Just like you know a plus b, a minus b, you can FOIL it, or you can just go and say, oh, it's a squared minus b squared because I know the formula. So it's so some formulas will be of that kind, and the other formulas will be very important, right? You will have to know them. I missed it. Anyway, going to the bottom. So let's go restart this.